Hello everyone, I'm Sang-Ri Yi, a postdoc at Sim Center, UC Berkeley. In Sim Center, we develop software tools to assist modeling and simulation of the regional scale impact of natural hazard. We think of our tool as a collaborative research platform where you can easily share your research outcome and also play with others. We follow basic performance-based engineering workflow, and as you can imagine, each of these boxes are associated with different kinds of challenges, and my work is one of the efforts to overcome these challenges. So let us think of high-resolution regional simulation workflow, seismic simulation workflow. We first need to generate high-fidelity structural model from some high-level inventory information, and we also need to generate some earthquake scenario. Using that, we perform nonlinear dynamic analysis, and the result is used for fragility function, damage, loss, and recovery modeling. And among entire workflow, we found that the most time-consuming part is nonlinear dynamic analysis. So we found the need to replace this module with some pre-trained surrogate model or a reduced order model. And my research is focusing on surrogate modeling. That means if we have a structured system with some input of interest and output of interest, we want to create a direct mapping between input parameters and output response. So surrogate modeling just works like a regression model. However, we have challenge because ground motion time history is such a high dimension variable. So instead, to avoid that, we just use the features of ground motions as input of our surrogate model. And then the problem is that our response is no longer deterministic. That means even when we have exact same ground motion features, we can still have different detail in the time history of a response, and then that creates some uncertainty in the response. So the task of our surrogate modeling becomes not only to predict the mean, but also to predict the variance accurately, because that's what is really important in the earthquake engineering. So among different alternatives, we explored stochastic Gaussian process application. The existing one relied on so-called replication. That means they needed to generate lots of samples that shares exact the same input values. But that was not possible in earthquake applications. So we were exploring no replication strategy, which basically first predict the mean, and then estimate the variance by measuring how much each sample is deviated from the predicted mean. And through some numerical examples, we were able to verify that the later approach can still give a robust accuracy while we can avoid the replication. And this is only one of the challenges among so many we are facing. There is a lot of room for your contribution. Thank you so much.